Hello friends, I'm back with the part 2 video of conjugate heat transfer analysis of industrial oven. The link of the part 1 video is given in the description. Let's start the video. Before that, please do like, share and subscribe. So in part 1, I discussed the applications of industrial ovens, geometry creation and mesh generation. An optimum mesh was selected for this proof of concept case. In this video, I will present operating conditions, revisit the folder structure and update the files, and launch the simulations, and finally post-processing will be discussed. So let us discuss the operating conditions first. The specifications and operating conditions. The working fluid considered is air and the material of the solid is aluminum. Both the inlets are specified with velocity inlet boundary condition with a velocity of 0.5 meters per second. Air is blown from these inlets with a temperature 453 Kelvin. The other boundaries are specified with pressure outlet boundary conditions. Now let us revisit the folder structure and check the operating conditions and update if needed. Let us revisit the folder structure. As the present case deals with multiple regions like fluid and solid, the first thing to check is whether the interfaces are created or not. That is fluid to solid and solid to fluid. This has to be checked first. Further, sometimes, though mesh is created successfully due to minor manual errors such as copy paste mistakes, STL file name mismatch, etc., the correct boundary faces are not identified. Hence, in that scenario, OpenFoam will group all the boundary faces as one group and save. So it is very important to check all the boundary faces with respect to our case and update them. So let us check this first. So we go to folder constant, then fluid and polymesh. Here open this boundary file. So here we see 7 boundaries, inlet 1 and 2, open 1, open 2, wall. So these names are from our current case only. This is fine. Then outlet, then this is the interface boundary, fluid to solid. So here all the boundaries are taken correctly and the interface boundary is also created. Fine, this is okay. Now we go to solid part, solid, polymesh, then boundary. Here we can check the interface boundary solid to fluid is created. So this is fine. Once these two are verified, then we go to 0 folder, fluid, and we check all these files. Let us open this file U. The internal field is initialized here with 0.1 epo minus 3 in z direction. So the boundary names are fine. So here the fluid to solid interface is given as no slip wall boundary. Inlet 1 and inlet 2, as explained, a velocity of 0.5 meters per second is specified here in z direction. And other boundaries are specified with pressure outlet boundary. Now we go to temperature. So the domain is initialized with uniform temperature 300 Kelvin. The inlet temperature is 453 Kelvin. So inlet 1 and inlet 2. Here we give inlet temperature of 453 Kelvin. So rest all are fine. Now let us open this file and revisit all the files once. So here the outlet open1 and open2 are given fine. No need to change here. Now we go to pressure. This is also okay. So in this file again, fluid to solid boundary is given here, and all other boundaries are fine. Let us open K. So we need to check this boundary fluid to solid, and then all other boundaries are updated correctly. Now we go to epsilon. Here to this is fine. This, there is no need to open this. This is created by the machine. So here too, the fluid to solid boundary is updated and all other boundary conditions are written correctly. So this folder is fine. Now we go to solid. Here the temperature. So the internal temperature uniform 300 Kelvin. The solid is initialized with temperature 300 Kelvin and other parameters here are fine. So here this is a solid to fluid interface. So this folder is fine. So the 0 folder is fine for us. In constant folder, all the parameters are fine here. I have verified it. Then you go to system. Then so the fluid, turbulent and other schemes are updated here. You need to verify this. Okay. So all these files are fine. So we go to control dict. So the end time is 1500 seconds. I would like to run the case for 25 minutes of process time, so that we, in real ovens the process time spans around 25 minutes. So I have taken that time with a delta T of 1 e power minus 2, and the right interval is for every 60 seconds the result will be saved, and rest of the parameters no need to touch. Now let us update the operating conditions. So here in fluid, let us check these files once. So here we are not giving any gravity, so this is fine. Then we go to momentum transport. So here we are using K epsilon model. So this model is updated here. So let us go to physical properties. As explained in this simulation, air is considered as the fluid. So the properties of air are updated here. Then the turbulence properties. Then the turbulence properties are updated in this file. The K epsilon parameters are updated here. This is fine. Then we go to solid. Here too, as we have considered aluminum as the material for the solid, the properties of aluminum are updated here. Now this is fine, so we are ready to launch the case. Now let us launch the simulation. Let us decompose. All regions. Okay, so here we can see I have given two processes. and then it is decomposed correctly. And okay, now we go to MPI run. Two, I'm using two processes. So now the case is launched on two processes. It has to run up to 1500 seconds. So once this is done, I'll get back to you. The OpenFoam parallel commands are given here. The case was launched on two processes and the simulation took 18 hours to complete 25 minutes of process time. I have created animations, so let's have a look. It can be observed that the hot air jets from the inlets collide and disperse in transverse directions. Due to presence of outlet and two openings, the air jets move towards the openings on either sides, where the pressure outflow boundary is specified. Hence, comparing the velocity and the streamlined plots, it is obvious that the air distribution is not uniform and resulted in poor heat transfer to the solid. The temperature of solid has raised by only 12 degrees in 25 minutes. It can be further observed that due to poor distribution of air, the heat transfer is less at some locations. For example, see this location here and at this end. Here the air distribution is not proper, so because of that the heat transfer is less. You can see here there are a lot of zones where the air circulation could not be properly distributed. So this is the reason why the temperature could not rise. This scenario emphasizes the importance of parametric studies of oven design using CFD. Uniform heat distribution can be achieved by carrying parametric studies using CFD. Various design parameters that can be considered are adding number of inlet nozzles on either sides, collocated arrangement of nozzles, this enhances circulation and mixing, inlet flow rates and blowing angles, various inlet flow rates and different angles can be tested, strategic placement of outlets, and velocity of the object or the body in white in the ovens. In general, in ovens, the body in white or some of the objects are moved through the oven at certain speed. So this speed also impacts the efficiency of the oven. Further, added to this, energy conservation plays a vital role in oven design. Measures such as recirculating the hot air from the outlets, insulation of the oven, this reduces heat dissipation and enhances uniform heating, and employing humidity controls, exhaust fans, etc. Some of the few measures employed to enhance energy conservation and save energy. So finally in this tutorial, both part 1 and 2, I discussed basically about industrial ovens and their applications, explained the case setup procedure in OpenFoam12, discussed the mesh refinement activities, explained simulations and presented the results. Once again, I emphasize the fact that extreme care is needed to set up the case manually as it is error prone. A graphical user interface like SimFlow or any other will be very useful and beneficial. So guys, That's all in this video. Should you have any doubts, please do comment. But before that, please do like, share, and subscribe. Thank you.